Alright, our next concept in this unit is going to be something called the ideal gas law. But before we get there, I need to continue the lecture where we just left off on talking about the combined gas law. And in the combined gas law, again, we took all of the gas laws, Boyle's, Charles, and Guy-Lusage's, and combined them all into one very large gas law, which you can find on your chem helper. We can use this gas law to pretty much do any 3-variable or 2-variable changing in conditions of a gas to be able to figure out its pressure, volume, or temperature if we know the other constants. Well, we're going to start talking about here on something called Avogadro's principle, and yes, this is the same individual that was able to determine that 1 mole of gas equals 6.02 times 10 to the 23rd particles of gas. Could be atoms or molecules, depending upon what the particles of the gas are. Well, one thing we had to do to be able to compare gases to other gases is to create a standard set of conditions. And that standard set of conditions is called STP. So when we have a gas at STP, that is implying that that gas is at standard temperature and pressure. And when we have gases at those conditions, we can then treat them to be very similar, and we can easily, doesn't matter where we're doing the experiment, we can treat those conditions to be set. Standard temperature for a gas is considered to be 0 degrees Celsius, the freezing point of water. However, we don't use Celsius much, so the key thing there is 273 Kelvin. 273 Kelvin is considered standard temperature for gases. Standard pressure, as you can probably already guess, is 1 atmosphere, or 760 millimeters mercury, 760 torr, 101.3 kilopascals, also in your chem helper. So when we have a gas that is at STP, we have found out something called molar volume. Any gas at STP, doesn't matter what it is, because we're going to treat every gas, we're going to treat it as an ideal gas. And therefore, any gas will follow these set of assumptions we're going to talk about towards the end of this lecture today. Any gas at STP, because they're all the same, we assume or know that 1 mole of that gas will occupy 22.4 liters of volume. If the gas is at STP. It doesn't matter if it's carbon dioxide, helium, hydrogen. If we have any gas at STP, 1 mole of it is equivalent to 22.4 liters. And not only that, 1 mole of it, 20.4 liters, that also tells me it's 6.02 to the 23rd particles. So 1 mole of gas at STP contains Avogadro's number of particles, and that also means it will occupy 22.4 liters of volume. Okay? So this is a set of, again, equalities that we can use in conversion factor problems. Let's take a look at that. On the next page here in your packet, on page 6, our first problem here says how many molecules of hydrogen are in 3.72 liters of gas at STP? Well, we have 3.72 liters of gas, and we are at STP. I can use molar volume is a technique that I can use in order to convert the volume of a gas into its moles. And that's exactly what we're going to do here. Since we're starting with liters and we're at STP, if I divide the liters by 22.4, that will give me the moles of gas. And within every mole of gas, there are Avogadro's number of molecules. Since hydrogen gas exists as a bonded hydrogen to hydrogen molecule, we call that particle a molecule. So we can utilize these numbers to be able to do these conversions if we are at STP. So 3.72 divided by 22.4 times 6.02 to the 23rd, and we get very close, so I'm going to have to round this number to 1.0 times 10 to the 23rd molecules. If you rounded it up from 9.99 to the 22nd. Okay, that's what we get when we round it up properly. All right, so that's how we're able to convert liters into number of molecules. Okay, so I'm going to pause the lecture now. I'd like you to go ahead and give B a try and try to do this problem, treating what we just talked about in the previous one. All right, this one's a pretty simple problem. Again, if we are at STP, we can use 22.4 to convert the moles of a gas into its liters. Again, it is not important to know the identity of the gas. Since we're going to treat all gases to be ideal gases in this unit, it doesn't matter really what the gas is to do a problem like this. All right, problem C, we get these decimeters cubed, guy. I apologize for that. That should have been liters. So a sample of oxygen gas, 5.6 liters of volume at STP. How many moles of hydrogen is that? And then D, what is the mass of that? So now, knowing the volume is 5.6 liters, go ahead and do C and D on your own. Restart the lecture and see if you've got those problems correct. All right. Now, we're literally doing the opposite of B in letter C. We now have the volume. Again, we're at STP, so I can use 22.4. So again, 22.4 liters is equivalent to 1 mole, and we get 0.25 moles of oxygen. Once we know the mole quantity of anything, we can then convert it into anything else. And the next step here, letter D, we're going to convert that mole quantity into a gram quantity by using the molar mass. And a quarter mole of oxygen has a weight of 8 grams. So that's how we can utilize molar volume as a conversion factor to be able to convert. Again, the key here is to be able to convert between the volume of a gas and the moles of the gas. We are using this 22.4 to be able to make that conversion. Okay? So part of your homework problems is now to do on page 7 in your packet. I would like you to do the odds on the bottom. You've already done 19, 21, and 23. I'd like you now to do the odds on the very bottom of that page, okay, utilizing questions like that, and go ahead and finish off the bottom of that after problem 23 on page 7. So finish up the bottom of that, and then you can check the answers in Canvas. All right, now I'm going to turn the lecture and we're going to say, now how do we convert volume to moles when we are not at STP? All right, now will be the focus of the rest of this lecture. And we are able now to use something called the ideal gas law. The ideal gas law is on the chem helper, and it's PV equals nRT. The purpose of the ideal gas law is to be able to convert the volume of a gas into its moles at any set of conditions. We can even use the ideal gas law if we are at STP. We'll get the same answer using the ideal gas law as we would using 22.4. However, if we are not at STP, we must use the ideal gas law in order to be able to convert the volume of a gas into its moles or its moles into its volume. But that is the purpose of PV equals nRT, is to be able to solve for between volumes and moles. Again, big P stands for pressure, and that can be in any units. It can be in atmospheres, millimeters of mercury, torr, kilopascals. The volume, which is big V, must, and I use the word must be in liters. And the reason why is this R, which is a constant. R is called the ideal gas constant, and the units of R are in liters. And this is why the volume must be in liters, so that the units properly cancel. The temperature is also in Kelvin as normal. So the temperature, we never use Celsius in the ideal gas law. It too must be in Kelvin as normal. And N is moles. Again, we use the ideal gas law to convert between moles, which again is letter N, and big V, which is volume. So we're able to convert between the volume of a gas and the moles using the ideal gas law. Now, the values of R, there are multiple R values, and it's based on the units of pressure. Whatever the units on pressure, that is the R. So if I have pressure in atmospheres, I'm going to use the R constant of 0.0821. We always use that number for R if we're in atmospheres. If we are in kilopascals, we're going to use 8.314. And if we are in millimeters of mercury or torr, because they are the same equivalent, we use 62.4. These are the values of R we'll utilize, based on what the pressure units are for the problem. But again, the volume must be in liters and the temperature must be in Kelvin. All right? Now, the big difference between the ideal gas law and the combined gas law is in the combined gas law, we are changing a set of conditions. We're changing the conditions of pressure, volume, or temperature. In the ideal gas law, there are no ones and twos because there's only one set of conditions. The combined gas law is when we have multiple sets of conditions. When we only have one pressure, one volume, and one temperature, we're going to use the ideal gas law instead. Okay? All right, so first problem. Calculate the number of moles of gas. So again, we're trying to find N, the moles. The volume is in liters, so that is good. We have the temperature in Kelvin, which is good, and the pressure is in atmospheres. So this is pretty much a plug and chug into the equation PV equals nRT. Go ahead and plug in the variables and solve for the variable requested, and when you restart the lecture, you'll see the answer. See if you get it correct. All right, I want to first show the setup of the problem. The pressure is 1.5 atmospheres. The volume is 3 liters. N is what we're solving for. R, key thing there, we want to use the R that is in atmospheres, which is 0.0821. Whenever we are in atmospheres, we're going to use that R value. And 300 Kelvin. The kelvins will cancel. When we divide over, the atmospheres will cancel, and the liters will cancel, and we're left with moles. When we're trying to solve for N, sometimes people make a mistake here. To solve for N and isolating it, we have to move the 0.0821 into 300 over, which puts it on the bottom. So our final answer should have been 0.183 moles of gas. Okay, so that's a first introductory type of problem that we can do utilizing the ideal gas law. All right, I'm going to pause the lecture again. I want you to go ahead and read problem 2 and go ahead and try to solve it. When you restart the lecture, we can go ahead and see if you got it correct. All right, in this problem, you'll notice is what will the volume be? So we're trying to figure out the volume now. We have 0.70 grams, which is not moles, this is mass. And we are at standard temperature, which tells us it's at 273 Kelvin, and we are at 150 kilopascals, excuse me. So, in order to use PV equals nRT, the R is a constant, so it's given to us. Temperature has been given to us. The pressure has been given to us. And we want to find the volume. So we need to know yet is the number of moles. Well, 0.7 can't be plugged in for N because 0.7 is not moles. 0.7 is grams. So the first step, for those of you that already have done this problem, we've got to convert 0.7 grams of nitrogen into moles. Now another thing that students mess up on this problem is, again, nitrogen is diatomic as a gas. It's N2, like many gases. So with that, we have to first convert the grams into moles. We can do that by knowing the molar mass of nitrogen. Doubling the atomic weight of nitrogen in the periodic table, we get 28.02 grams. So taking 0.7 and dividing by 28.02, we get roughly 0.025 moles of nitrogen. So now I'm ready to plug and chug everything I know. The pressure is 150 kilopascals. The volume is what we're trying to solve for. The moles is 0.025 moles. Because I'm in kilopascals, I need to use the 8.314 R constant, and the temperature is 273 K. To solve for volume, we will multiply 0.025 times 8.314 times 273, and we're going to take that number and divide it by 150. And we get a volume of 0.38 liters. Again, whenever we solve for volume in the ideal gas law, we're going to get liters. because that is what the volume measurement is in the ideal gas law. Okay, so that is how to do the ideal gas law. And again, it's simply plug and chug. The key thing is to make sure the units match and you select the correct R value based on the units of pressure. All right, problem 3. A sample of oxygen gas has a volume of 7.84 cubic centimeters is actually a milliliter. So 7.84 milliliters at a pressure of 71.8 kilopascals and a temperature of 25 degrees Celsius. What will the volume of the gas be if the pressure is changed to 101 kilopascals and the temperature is changed to 0 degrees Celsius? Right away you can identify that the temperature and the pressure is changing. Whenever there are changes or there's multiple pressures and temperatures, we are not going to use PV equals nRT. This is only when we're given one set of conditions. When we're given multiple set of conditions, we cannot forget about the other gas laws we just learned. So this is screaming to use the combined gas law. So the pressure is 71.8 kilopascals. In the combined gas law, we do not have to have the volume in liters. We can keep it in milliliters. We just have to make sure that it's milliliters on both sides. However, the temperature must be in Kelvin. We never plug in a Celsius. Now, if you were to change the volume to liters, it's perfectly fine. But we don't have to. But the temperature must be in Kelvin. Okay? The new pressure is 101 kilopascals, my fault. We're trying to figure out the new volume, and the temperature is changed to 273. Again, the temperature must be in Kelvin. So going ahead and doing the cross multiplication, we end up getting a volume now of 5.1 liters. Okay? So again, we can't forget all of the gas laws from last week. Most of the homework will involve ideal gas laws, but sometimes you might be throwing a curveball, and you got to be able to go from one gas law to another based on what the problem requires. Okay? All right, on the next page, there are a couple other deviations that we can use the ideal gas law, and one of these deviations is going to be the laboratory for this week. We're calculating the molar mass of butane. And the deviation is this. Big M stands for molar mass. Molar mass is defined as the mass of a gas sample divided by its moles of gas sample. Well, that means big M is equal to little m over n. Since n is in the ideal gas law, if I rearrange and solve for n, I get little m divided by big M. What I can now do is in the ideal gas law is I can now do a substitution and get the little n out of the equation. Why would I do this? Well, the purpose of this is so I don't have to do multiple steps. I can figure out a new equation that I can plug in, and I don't have to figure out the moles of the gas. If I know its mass, I can use that to figure out its molar mass directly. So if I move the big M over to the other side, I end up getting the molar mass times the pressure and volume of the gas equals the mass of the sample of the gas times the ideal gas constant times the temperature. So this is a different variation of the same equation, and we can now use this equation to figure out the molar mass, and that's what we're going to do in laboratory this week. I can figure out the molar mass of the butane gas. If I solve that equation for big M, I get the mass RT over P over V. So I can figure out the molar mass of the butane if in the laboratory I can know the mass of the sample, the temperature of the sample, the pressure of the sample, and the volume of the sample. And if I pick the correct R, I can now plug in all 5 of those numbers and I can experimentally figure out the molar mass of the gas, which is what you're going to be asked to do in the laboratory for this week. Another variation of the ideal gas law is if I take this equation, right here, this one right here, if I move the V over and put it under the M, I get M over V. Mass divided by volume is density. So I can now replace M over V with the capital D, which stands for density. And now we have a different variation of the ideal gas law in which we can use it to figure out the density of a gas. So these are just different variations of the same gas law we can utilize to figure out the density or the molar mass of the gas if we want to. Okay? So let's look at question number 3. What is the molar mass of a pure gas that has a density of 1.4 grams per liter at STP? So we see the keyword density, so we need to utilize the top of the equation right here that we just figured out. So go ahead and I'm going to pause the lecture now. Go ahead, plug and chug, and see if you can figure out the molar mass of this gas if we know the density of it. All right, plugging in all the variables. I used 1.4 was given, grams per liter. I used 0.0821, which means then the pressure that I have to use is in atmospheres, and standard pressure in atmospheres is 1, and the standard temperature for gases is 273 Kelvin. The liters will cancel. The liters in the density and the gas constant cancel. The kelvins in the gas constant and the temperature cancel. And the atmospheres cancel. And what we're left with now is grams on top over moles on the bottom. And that is the units for molar mass. So we can see that units do work in this equation. And the molar mass of this gas is 31.3 grams per mole. Okay? All right. One last thing, that's the mathematics of the ideal gas law, which is what the homework mainly will focus on, but there are some conceptual applications I'd like to talk with you guys real quickly about to wrap up this lecture and concept. And believe it or not, there's only one last concept left for next week, which is gas stoichiometry. All right. A real gas is what it's like in real life, laboratory. An ideal gas is assuming a perfect set of conditions, which can never happen. But some gases behave better than others. When we treat all gases as ideal gases, some gases behave much more ideally than others. Well, there's a couple of assumptions that we make whenever we treat a gas as an ideal gas. The first is, so that's the one thing in this container here, is the space the particles take up. In ideal gas law, we assume they take up no space, but in real life, they take up a small amount of space. The second major assumption is these particles contain protons and electrons, so they have positive and negative particles. Same thing does another gas particle. And those particles then can have electrical interactions. Well, in real life, they have small intermolecular forces. But in real life, but in an ideal setting, we assume that they have no interactions. And therefore, when the gas particles get close to each other, they really do not attract or repel to each other. In real life, they do. So gases that tend to follow this assumption the best are the noble gases. Okay, the noble gases are very unreactive, and they do not have very large positive negative charges to them. So the noble gases, because they really don't interact and want to react with each other, they tend to follow the ideal gas law very, very well. So the very light, small noble gases like helium and neon really follow the ideal gas law quite well. It would be ideal gases to utilize in any situation for making the whatever mathematics we get in the lab, we would get a really good value that the ideal gas law could approximate because the gases are following these assumptions that we assume to be true. One last thing to talk about is conditions. Which conditions favor ideal behavior? Well, through experimentation, it is found that when we have low temperatures and we have high pressures, these conditions are the absolute worst for the gas following a gas law. And if you think about it, why? If I have a gas under enormous pressures, we are squeezing the particles closer and closer together, which means they are doing a worse job at the approximation where they're not taking up a lot of space. Also, if I make the temperatures really cold, I'm getting close to condensing the gas and making it into a liquid. So when I put gases under enormous pressures at low temperatures, I am able to, in an experimental setting, actually liquefy the gas or condense the gas into a liquid. Well, no wonder the gas doesn't follow the ideal gas law very well. It's because it's closer to the liquid state than it is the gaseous state. So what conditions, if I'm able to control the temperature and the pressure of a gas lab, I'm going to want to have the temperature as high as possible and the pressure as low as possible. And these two conditions will make this gas follow the ideal gas law better. And therefore, whatever we get utilizing the ideal gas law, whatever mathematics we get from it, we're going to get a number that is very close to what we actually calculate. So these are things that we can look at as conceptual questions of what type of gases will favor or what conditions will favor where our numbers will follow the ideal gas law very well. The benefit of the ideal gas law, PV equals nRT, is that it's a very simple equation to use. However, if the gas that we're using is very big or it's not a noble gas, it might not follow the gas law very well, and the number that we get from it does not match what it really is like in laboratory. A way around this is we can then make the conditions of the experiment have really high temperatures and really low pressures, where even a gas that doesn't follow the ideal gas law very well could follow it based on making the conditions a favorable set of conditions. So these are types of conceptual questions you must be aware of that you might see in the next exam, and are probably the harder questions because you got to think about what is causing, do I want the gas to follow the ideal gas law or not follow it? What is the question asking? All right, so that's ideal gas law. The mathematics is pretty simple. The conceptual application, you just got to kind of think about what will the gas follow the gas law very well or will it not? Will the numbers give me good numbers or not? And those are things you got to think about, and that's what makes it a little bit harder. The math is a lot of just mindless plug and chug and solving for the right variable, and a lot of you are showing me you can do that in the stoichiometry and other units, so that should be pretty simple mathematics to follow. All right, that is the ideal gas law. Again, thanks for listening. This is the only lecture for this week, so if you had to break it up or chunk it up, hopefully you did. But now you've gone over both the math and the conceptual applications of the ideal gas law. Here is when I have a container of a gas. The volume of the container, let's say it's 1 liter. Well, the volume is truly the amount of space that the gas can travel through. Well, the true space that the gas can travel throughout is really the volume of the container minus the volume of the space that the gas particles take up. If I were to condense all these gas particles and tightly pack them as tightly as I can get, they probably would all get all together in this little box right here. So the true volume that the gas can really spread throughout is really 1.0 liters minus that little square of all these gas molecules. If I could squeeze them together and figure out what that space is, then that would give me the true volume of the gas. Well, a big assumption that we make in the ideal gas law is we assume that the gas particles take up no space. And if they take up no space, the volume of the container is the volume of space that the gas can travel throughout, and that is the assumption that we make. Okay? Now, in real life, it's not. It's a little bit smaller than that because we have to subtract off the amount of room that the particles take up themselves. Now, if we think about it, which gases would be the best at following this assumption? Would they have small molar masses or they would have large molar masses? Which gases would meet this approximation much, much better? And hopefully you are saying small. So the smaller the gas, the better it is at following the ideal gas law, because it does not take up nearly as much space as a larger molecule will in the container. So the smaller a gas is, the more ideal it is.